Good morning or good afternoon, depending on where you are in the world. Welcome to today's webinar. I'm Sarah and I'm the Content Marketing Manager at SystemWeaver. We're very glad to have you with us as we explore how an integrated system design and software PLM approach can accelerate compliance across functional safety, cybersecurity, and ASPICE. Today's session will be led by Dr. Ahmed Majeed Khan, who is the VP of System Design at SystemWeaver. If you have any questions, please ask them in the Q&A and Ahmed will answer them after the presentation. Welcome.
Thank you, Sarah. And hello, everyone. So here I get a little ask if my screen is visible with a SystemWeaver logo before I proceed. Can any of you confirm, or Sarah, is it there?
Yes, it is.
IT check. All right, perfect. All right. And then, yes, it has told me that audio is there too. So we are good. The topic of today's webinar is that an AUTOSAR-compliant Immobilizer manager, system design and product lifecycle management with functional safety, cybersecurity, and ASPICE assurances. Sounds impossible, right? Let's see how we do it. So here's the agenda. We'll begin with the introduction and then go into the design principles for automotive system design, what are the considerations and nuances. From that, we'll get into software product lifecycle management, or I'll call PLM as its abbreviation, its requirements and challenges. From that, we will directly jump into our real-world case study of building an Immobilizer manager, which would combine multi-domain solutions by relying on the best practices from these two domains of system design and PLM. At the end, we'll summarize and conclude. So let's begin with the introduction. STV was something in the clouds, fuzzy. I mean, what would it actually mean? But the fact remains there that automotive industry is paradigm shifting. Cars are no more built. The quality and the market aheadness or the innovation parts are no longer dependent on the mechanical aspects of the vehicle, rather that's shifting to software. And then when we are talking about software, there are like widespread, literature on the speculation that software is going to account for over 90% innovation in the future of automotives. So here, when we talk about there are three main aspects which would require key attention: scalability, collaborativeness, and product focused with enterprise performance. So that's something we'll see how it would impact these three assets. These three facets would play a key role in building the SDVs of today and tomorrow. What's the problem? The problem is that traditional or usual development processes, tools, and architectures are no longer sufficient to manage the software development. So software complexity is paramount in cars, or had always been complex. So it reminds me of a 2010 IEEE study where the lines of code of cars were compared with the most sophisticated machines of that time, which included Boeing aircraft, space shuttle, and things of that nature. And cars surpassed all of those. That was even before the SDV era, 2010 time frame. So under SDV, this problem's gonna go skyrocket anyways. On the course, there are safety and security concerns, and then there is adoption of new architectures, zonals, gateway ECUs, the high performance compute nodes, and so on and so forth. So that adds to the challenges. So if there are no agile, customer-centric processes and solid lifecycle management and compliance, it could turn a plethora of issues down the line. So think of OEMs switching back from zonal to traditional architectures. Happened last year, right? Think of top OEMs bringing in-house the software development, leading to the software factories, and then like kind of reverting back from that decision, back to getting JVs, back to getting outsourcing paths. So the key here is that the greatest weapon in our arsenal to combat these problems can turn to as our biggest liability if not done right. For automotive software, this problem gets even amplified because it's not just about the code, it's also adhering to a web of standards like ISO 26262 for safety, 21434 for security, and then for quality management, ASPICE kind of things. And then these standards are not only interdependent into each other, but they are also constantly going through an evolution. So interdependence and then intertwining part and then the evolution part makes the problem even more complex to solve. So we call it the problem pro element of automotive software development. And then we are living in a world, in an interesting world where software and hardware built in a specific territory or geography is not suitable to be deployed for production cars in other areas. So those software restrictions would require, and the restrictions on the hardware for SDVs would create further issues down the line on version management, project management, like what components are in there, ASPICE, the Cyclone DX standards incorporation into the automotive software PLM practices, and so on and so forth. So that makes it problem pro max, right? So with that background, keeping that in mind, let's look into the key considerations of automotive system design. So for the system design, first example we got from AUTOSAR Classic, you know the design flow, that it all begins at the requirements which come from several different areas like stakeholder, legal, and so on and so forth. And they are used to build classic components. Then based on that, classic interfaces are defined, network is laid out, and that work happens in parallel when hardware is built too. So the ECU work is built in parallel and the software is designed to save time. And then when the hardware is ready, we start allocating software components on actual ECUs, which makes it an allocated design. And then from that point, you define external interfaces, look at our inter-ECU communication, generate signals, the system signals, do the network part of it to eventually get a system description. On the AUTOSAR adaptive, the flow is kind of similar, but here, there are service interfaces, not signals anymore. So services are built based on the requirements and then are deployed. And then based on the deployed services, adaptive components are built into executables, which are put into machines, which is like kind of high performance ECUs and stuff. So called as machines in the adaptive world. And then after service interface deployment, ARXML is generated and this part of the world creates a system manifest. So keep that flow in mind, and that's something which we see most ECU and the AUTOSAR-based programs they are taking as a baseline. Here, let's about time to look into the software PLM requirements and challenges. So the first one is cybersecurity. So cybersecurity mandates a new lifecycle approach by creation of a CSMS, which threat and vulnerability management are in there. So this needs to go in all life cycle of the phases, beginning from the concept to development, validation, and then when even the car is on the road. So if we put it in a traditional V model, so vehicle design, system, and then implementation, and then the testing for that, and then the homologation or road testing. But even when cars are on the road, due to requirements of continuous software updates like OTA and stuff, cybersecurity would become an inherent part of the design when vehicles are running there. When cybersecurity comes in, the international standard for its compliance is 21434 ISO SAE 21434. So when we look at the structure of the ISO, you would see that a cybersecurity starts at the top org level and then goes down to the project level, and then there are product specific dependencies, and then thorough part of it. So from a software PLM perspective, all these components need to be part of the design cycle when the software is actually built and designed. The next one is functional safety. And in the functional safety, you would know that there is functional safety concept, technical safety concept, validation pods, HORA, FDA, FMEA. Those are the usual suspects, but also there is a conformance management, the standard fulfillment, the contextual reviews and those. So that needs to be inherent in the PLM, in any robust software PLM design. And then when we talk about safety, the corresponding compliance comes from ISO 26262. And then when we zoom into 26262, there is a product development at system level, and then it goes to hardware and software levels. And then there are supporting processes across the organization which need to be met. And then there are ASIL levels which need to be defined and implemented for several components. So from an implementation perspective, all these components need to be part of the lifecycle design when this software is built and tested. For quality, ASPICE is the usual suspect. So ASPICE comes up with its own requirements, where there are requirements coming from systems engineering, and then they trickle down. So we add systems engineering, and then that trickles down to the we add software engineering, hardware engineering, and then there are organizational and life cycle management processes to comply with ASPICE. And that's ASPICE alone. We discussed that standards are interdependent and evolving. So if we put ASPICE with cybersecurity, there is a process reference model already available. And then we can see that cybersecurity has been pulled into the very processes. So there is a cybersecurity process group, but then it goes into the very supporting processes or the organizational processes to get the most value of it. So with that, now let's dive into actual design and see how these multi-domains can be connected to actually build an immobilizer manager. So Immobilizer, those of you who do not know, represents anti-theft detection system in the car. It receives driver's intentions and then senses the environment, and before making a judgment call if it is okay for the engine to start or not. And here I'm showing the decomposition of the immobilizer. We based it on AUTOSAR to remove the element of subjectivity from it. So we based the design on the ARXMLs that we get from the working group application interfaces, or AIF, of the AUTOSAR consortium. Just to be, when we talk about an AUTOSAR compliant immobilizer manager, we don't have to talk about what it is connected to, what are the ports, interfaces, what type of data is being traversed, because all that comes from the blueprint of that ARXML. So with that settled, the first beginning part is building the electronic system architecture. And then here you want to have a design graph on how the components are connected to each other at the function level. So the function realization happens at the electronic system architecture. And once you have that function, those functions ready, you want to zoom into each function to actually build the requirement distribution, the function requirement block distribution. So each function, what kind of activities are actually happening inside that function. Here, the traceability becomes very important for the requirement part, that you want to be aware that what requirement is coming from what perspective. Like, for example, is it a legal requirement coming from UN per se, or 155, 156 for safety security, 171 is in vogue now for version management. The ISO 26262 has its own requirements, and then stakeholders have their own requirements. So you want to see what's the origin of it, and then that needs to go down to the design phases where the actual functions are being performed. Once this system architecture is available, you want to go to the system design, and it is unallocated at this point because, as I mentioned, the hardware is built in parallel, and you do not want for your software design to wait for that. So you are looking at how your system would look like without doing an actual mapping to the EC. So for the first part of it begins with a component graph where you would build a component and start working on its interfaces, how it would interface with the other components. And then once one component is there, you want to build a design graph of your all components and their connectivity. And here the communication management is one of the pivotal role, that how those components are talking to each other. And you want to be mindful of the requirement traceability and the mapping elements to ensure that your requirements are triggered downstream in the required or desired fashion. Another interesting aspect here is that it's gonna be in most of the real world scenarios. It's gonna be a mixed architecture design. So AUTOSAR classic and adaptive would be lying in the same world in the same system. So we introduced another adaptive component here, and then this is one of the key challenges that we hear very often, is that the translation of signals to service, so they can traverse in the two worlds of adaptive and classic, and vice versa. So I mean, we in fact, like at the ELIB, and then prior to that at the AUTOSAR Open Conference, several OEMs presented about how they actually solve this problem. So here you want to have a model at the center where signal to service or S2S translation capabilities are present for the two worlds, classic and adaptive, to talk to each other. When this is done, the hardware is ready. So you will start mapping your components on the ECUs, and that's where the design graph comes into play, where what components have been mapped to what ECU. So that's in there, and then how they are talking to each other. Here, since the hardware is ready, so system consistency, and then trickling the system down to individual ECUs. So ECU consistency, and then these signals, how they are connected to each other. If the sender receiver ports map to each other, what are the port properties? All these things need to be part of the design to ensure a smooth and streamlined process. Here again, the adaptive and classic worlds are going to coexist. So it's going to be a mixed architecture, and then you want to look at network topologies, how the worlds, how different ECUs are connected. Where is Ethernet, where there's a VLAN, if it's a CAN connection, and so on and so forth. And that translation would require an S2S model at this level to ensure a streamlined communication between these mixed architecture domain. Cybersecurity is the next one. So you want to begin by building a system model around the areas where cybersecurity needs to happen. So I mean, or cyber, if there are requirements to do cybersecurity at all the system, then like I mean, still the labels or the cybersecurity requirement at each of those domains could vary based on what kind of systems are under consideration. So once that model boundary is defined, you want to go with a security graph which takes your assets or what needs to be protected, creates damage scenarios for that, threat scenarios, attack paths, and then map them to design functions. So for example, for our Immobilizer example, one of the damage scenario could be that the Immobilizer key has been compromised. And for that, the violated property would be the violation of confidentiality. And then the description would be that the confidentiality is lost because of a compromised key, and then which could create a negative impact for user and vehicle. So that kind of modeling needs to go into a grid where damage scenarios have their impact mapping, the impact rating, the damage scenario descriptions, and with that, you can have an infrastructure to do thorough in compliance with ISO 21434. The next one is functional safety. And for the functional safety, the beginning part is us building a safety graph where the safety requirements are connected to hazards, hazardous events, and then eventually to the overall safety goals. So for example, in our Immobilizer example, one of the hazard could be that prevention of the engine unauthorized start, and then that can happen in several different ways. If I map that to the Immobilizer case study, then that could easily be one of the hazard could be that Immobilizer fails to prevent an unauthorized engine start. And then in that, if we kind of zoom into that scenario, the vehicle state could be that the vehicle is static or moving. So two different goals and two different fail-safe states in each of the scenarios. And then the event could be that either there is an RF interference, which impacted the relays functionality to malfunction, or a thief could have cloned the key, or the key is not working. So there can be several different ways in which a fob or the key function is badly impacted. So you want to know in your grid that what are the events, what is the easy level for which a specific event is impacted, and then how it trickles down to your safety goals with providing one-on-one mapping between the requirements and the safety goals, going through hazards and events. And with all of that, you can have an infrastructure to do HORA, FDA or FMEA in compliance with 26262. ASPICE is the next one, quality management standard. So with ASPICE, one is that a process management area. So, the organizations do have their processes, different processes, internal processes, and then there are ASPICE requirements as well to do some kind of tasks. Like, for example, we started with building our system relying on different set of requirements, and the requirements were coming like from stakeholder requirement, stakeholder, legal, functional, and several different areas. So in the ASPICE world, all of those steps are going to map to requirement elicitation, like per se. Similarly, I mean, if you do define your components or external interfaces or generate system signals for external interfaces, this is like kind of in the ASPICE world, this is system architectural design or system architectural analysis and requirement elicitation if there are activities like definition of design requirements and so on and so forth. So that mapping is critical to be mindful of, and then there is a process standard fulfillment element attached to it that for auditors and for internal compliance meeting requirements, you wanna ensure that the internal activities which are performed in an organization are actually mapped to the standard. And then, there needs to be an automation in that too, that if the process is used for several different projects, or if the process it needs to be cloned, or if there is a change in the process, or if there is a change on the organizational activity, that thing gets inherently built into the design flow to ensure to prevent manual activities and avoiding redo on those kind of parts and avoid human errors as well as you go down that journey. So that process management and standard fulfillment need to be part of the inherent design to ensure quality managed product. Beyond that are miscellaneous SPLM activities. So like, for example, you want to have a network topology to look at the network. You want to have consistency checks. Like, for example, if a sender port is 32-bit and the receiver port is 16, how they can talk. So the system needs strength that, okay, there's a mismatch, or a sender receiver unconnected port is present. Then why that port is in there. And then, like, I mean, there needs to be strength in the design tool to ensure that right set of system has been put into play. Documentation is another important aspect. So documentation would be needed for safety compliance, security compliance, internal things, and all those activities. And then, like, I mean, if there is a change in one of the areas, like a port is changed, or the design requirement is changed, or a new requirement came in, then you want to ensure that that change is trickled right to the downstream activities, going through the consistency checks, passing through that, connected to the safety security goals, and then trickling down in the documentation to all that, making all that flow automated. And then there are pie charts. Pie charts could be showing state of affairs for different levels. It could be what is your test coverage, what kind of requirements have actually been traced or not, what parts of software is coming from countries of concerns and not, what part of the software which is coming from countries of concerns as the US DOC ruling, then how much Tara has actually been built on that software, so on and so forth. So all different views and activities to ensure that you have a streamlined PLM activity when you are working on the design. So for that, cross-domain data connections are required to ensure control and efficiency across the whole process. So with that, let me summarize and conclude. So streamlined data communication and storage is the key. So if data is incomplete and scattered in silos, it would make it not scalable, not a scalable design. If there is a difficulty in tracking and tracing the changes, it would make it like kind of impossible to be compliant with international compliance requirements. If the processes are not clear, it would lead to an inefficient way of working, like, I mean, data flying in silos through unclear processes, different teams working on different areas, and then data flying back and forth. So with that difficulty in adopt, that would make it extremely difficult to adopt to the technologies that SDVs are bringing forward. As opposed to that, if the design is consolidated, centralized in a collaborative and singular environment, then the streamlined part of the communication and data storage would lead you to a holistic product model where change management is inherent, version management is inherent. You can take several different reference architectures and trickle those into products, and all that could be taken care of the central information model at the center of the product. So to be successful in the SDV world, we looked at system design, and then we looked at several different PLM activities like HORA, FTA, FMEA, so on and so forth. But there is beyond that too. So version management requirements are coming up with our 171, and that's like already due in a year or so. So if a software version is changed, you want to have a track for forensics, and then you want to maintain that for extended periods of time to be there. And then there are reference architectures, tried, tested parts of the product which you want to reuse for other components, of course, by building other components or taking or removing out, but something built, tried, tested, validated, you want to reuse that into the variants, and then the configurations as well. And then apart from the usual activities, you want to have your documentation, the standardization compliance, the process support, the traceability from requirements down to validation, and on the up parts of the between connecting left and right parts of the V. So that, and then if all of that is in a single collaborative environment, so I mean, people are working in real time. They are not, it's not like Excel sheets or the notepads or ARXMLs flying back and forth. So everything is real time, all in a single integrated repo where there is a change in a specific area, trickles down to all different areas, and then already highlights the impacts with consistency checks or checks built into the tool, and then like all that happening in real time. So all the development organizations become aware of the changes trickling down the line. So with that PLM process built for system design and safety security areas is something which can make the process very streamlined and to ensure a success in the SDP world.
Thank you so much for joining today, and thank you, Ahmed, for the good presentation.
Thank you, everyone. Cheers. Ciao.
Bye-bye.